Welcome to One Chemistry. We are seeing organic chemistry concepts. In this video, we will see Birch Reduction. It's an important organic naming reaction. We will see basics and mechanism and fully solve 33 examples. Stay tuned. Let us see what is inside this video. First, we will see what is Birch reduction and the mechanism behind the reduction reaction and the reaction types, how Birch reduction helps and how Birch reduction reacts differently because you are using the reagent, how the reagent interact with the other type of reactants. The four types basically. More important thing is you will see 33 fully solved examples from various examinations. It will be very useful for you. Stay tuned. First things first, we will see Birch reduction, basics of it. What is Birch reduction? In the standard example, lithium and liquid ammonia you are using as the reagent with alcohol. If you use those reagents with benzene, you have reduction at 1,4 carbon, basically 1,4 reduction. Here, lithium and liquid ammonia form a complex kind of reagent. Basically, it's a solvated electron. You can imagine multiple ways, but simple ways like coordination of ammonia with electron. The metals also can be various: sodium, potassium, and lithium. Lithium known for its activity, so lithium is the dominant one. Some cases, potassium and sodium will be used. Then the mechanism. Here electron in ammonia you are using. So electron transfer happen. Basically it's a set reaction. Single electron transfer reaction. So electron transfer. So electron mobility happen. It form radical anion. It will form away because radical anion both are electron. It try to form away as much as possible. So it form para relation. That's what 1,4 relation. Anion quenched with hydrogen form reduction. Then radical again gain the one electron through set mechanism. It form anion again. Then it quenched with H plus form the final reduced product. The concept you have to learn from the mechanism is basically you are reducing the first carbon and fourth carbon through set mechanism. Then the very important thing, how you are classifying Birch reduction. It's basically 4 types of reduction. Here basically I given 4 types. Technically it is not a Birch reduction, but you should know the similar reaction to know the advanced synthesis. Here 4 types: aromatic ring with electron withdrawing group, electron donating group, fused rings, heterocycles. Then dienes also will react. So diene reacts. So diene with reagent. Then alkyne, which is triple bond. Then conjugated ketone. You can call it as enone or alpha, beta unsaturated ketone. We will see everything one by one individually to have better understanding. Here Birch reduction. At first Birch reduction with electron withdrawing group. Electron withdrawing group basically stabilize the anion. So anion can form near the electron withdrawing group. Basically electron is the nucleophile here. It can attack anywhere, but it attack in such a way that form anion near the electron withdrawing group. It's a stable architecture. So through single electron transfer mechanism, that is set mechanism, the electron transfer, you have radical and anion both form para position. Then anion quenched by H plus form hydrogen, the reduction at the carbon near electron withdrawing group. Then radical is there. Again the electron transfer, it form anion. Radical converts into anion. Then anion quenched with H plus. You have final reduced product. The electron withdrawing group can be cyanide, nitrate, carbonyl, acid, amide. Basically a carbonyl structure or electron withdrawing groups. So if you use electron withdrawing group, you have 1,4 reduction. Then the similar but opposite example, electron donating group. Here electron is the nucleophile, same story, but it cannot form near electron donating group because both are same charges, so repel each other. or you can say both can increase the charge density. Less charge is more stable. So anion form away from the electron donating group. So anion forms, so basically a radical anion formation through set mechanism. Anion quenched with H, reduction happened. Then radical is there. Radical abstract the electron from set electron transfer mechanism. Again it become anion. It quenched with H plus. You have the final product. So basically you start from benzene. Loss of aromaticity happened. So 3,6 reduction happened here. Then the next type of reaction, Birch reduction with heterocyclic. Here quinoline is given. Quinoline reduction with lithium and ammonia. Reduction happen at the nitrogen ring, which is pyridine ring. 1,4 reduction happened. Why the pyridine ring? Because attacking species is nucleophile, which is electron. It is always attack the ring with less electron density. B is less electron denser because of electronegative nitrogen. Here two types of regioselectivity happen because B ring is selectively reduced and it reduces only on 1,4 position. So it's an important two-step regioselective reaction. So Birch reduction also work in the heterocyclic compounds. Then the next example, you have naphthalene, you are using lithium and ammonia. The reduction happen like benzene, 2 benzene ring reduce, 1,4 position. Basically a 2 consecutive Birch reduction reaction. If you are interested, write mechanism separately. You will end up with similar setup. The system is basically 2 benzene rings fused together. So reduction happen on both rings on 1,4 and 5,8 position. It's a double Birch reduction. The concept you have to learn here is Birch reduction, the reaction continues until the possibility of Birch reduction. Then Birch reduction in alkene. Technically it's not Birch reduction, but reagents are same. So you should know it's a kind of Birch reduction. If you know it, it will be easy for you to synthesize bigger or total synthesis reaction. Here I given conjugated diene. Second position you have substitution. So electron attacks, radical anion form. It form from away position. Radical and anion are separated. Anion quenched with H plus. You have hydrogen, there is reduction. But double bonds are switched. Then the radical is there. Again the electron addition happened through set mechanism. Anion forms. Finally it will be quenched with hydrogen plus. You end up with 1,4 reduction. So kind of 1,4 reduction. Starting from diene, you end up with kind of rearranged diene. So final product you have is 1,4 addition product. The concept you have to learn here is which reagent is active. It can reduce conjugated diene. Then the next set of reaction, Birch reduction in alkyne, that is double bonded compound. Here you have butane, you are using lithium and ammonia. Similar radical anion forms because you are using double bond, which is pi bond, separated as radical anion because you are supplying electron through set mechanism. Then the anion forms. So the possibility of splitting here, but anion and radical is the same charges. So it has to be repelled. To avoid the repulsion, the bond is twisted. CH3 goes away. It forms trans radical anion. Then the anion quenched with H plus. Radical also quenched with H plus. Final product you have triple bond compound reduced to double bond with the trans product. The trans is selectivity. Selectivity achieved due to the repulsion between radical and anion. Then the final type and very important one, conjugated ketone in Birch reduction condition. Conjugated ketone basically a alpha, beta unsaturated ketone. So Michael kind of addition reaction happened. Electron attacks, bond mobilize. You have O minus. The minus charge stabilized by electronegativity of oxygen. Then the O minus quenched with H plus form alcohol. Then again set mechanism, electron donates, you have anion. Then the anion again quenched with H plus, it forms hydrogen there. So alcohol, which is enol, it can convert to ketone. So Michael addition reaction kind. So you start from conjugated ketone, end up with ketone. These are all technically not Birch reduction, but you should know because of similar reagents. Next, very important thing, we are going to see 33 fully solved examples. Why so many examples? Because problems are best way to learn. It will give different perspective to the same question. You will be a better problem solver. Let us see the first example. Starting material is anisole benzene with OCH3 group. You are adding lithium, liquid ammonia in acidic condition. You should find what will be the final product. Here OCH3 is there, it is mesomeric in nature, it is electron donating. So you should expect reduction happen in the 3,6 formation. Reduction happen. Then acidic condition you are using. So O-methyl become OH. So ether CO bond cleavage, alcohol forms. You have alcohol and alkene, it's a enol. So keto form will form. So ketone will form. It is a keto-enol tautomerism. Then H plus attacks, you have hydrogen elimination, form alkene. The driving force for the formation of alkene is conjugation because conjugation gives more stable product. The concept you outline here is always focus on the reagents and selectivity in the Birch reduction. Then the next example, you have benzene. In ortho form, you have ester and methyl group. You are using lithium and liquid ammonia. You should find what will be the final product. Here the interesting thing is electron donating and withdrawing group in the same ring. How will you identify a product is the key identification. So practically you have to find the middle ground between ester and methyl. Ester contains carbonyl, it's a electron withdrawing group. Methyl is electron donating, it's a hyperconjugative in nature. So what will form? So double bond form near the methyl group but form away from the ester because carbonyl can stabilize the anion. You end up with final product. Basically two set of reduction happen. The relation and numbering given for only information, not with IUPAC nomenclature. So acid promote 1,4, methyl promote 3,6. Here one additional fact you should know why ester is electron withdrawing. It has sp2 hybridized carbon. The electronegativity, if you look at it, sp is more electronegative, then comes sp2, finally sp3. So sp2 is more s character than sp3, so electron withdrawing in nature. The concept you have to learn here is whenever you presented with multiple functional group, always find the common ground and find the correlation between them, predict the final product. Then the next example, here you have alpha cyanonaphthalene, cyanide in the alpha position. You are reacting with lithium and liquid ammonia. You should find what will be the final product. Here two regioselectivity happen. First you may wonder where the reduction happened, A ring or B ring. Here I given labeling for only identification. Here attacking species is electron. So electron is negative in nature. Obviously attack electron less denser ring because both are opposite to each other. Here cyanide is the electron withdrawing group because of sp carbon. So the electron density of the A ring will become less. So A ring will attack first. So the reduction happen at the A ring. Then the next question comes where the reduction happened. Here cyanide is the electron withdrawing group. So 1,4 reduction happen because cyanide can stabilize the anion. So final product is reduction happen with the A ring in 1,4 position. The concept you have to learn here is in the fused system you identify the electron density to identify the required product. Then the next example, you have benzene and side chain you have alkene. You are reacting with lithium and liquid ammonia. you should find what will be the final product. The reaction is little bit tricky. The starting metal is styrene. The side chain is alkene. Alkene, you may consider it as electron donating group because of pi bonds and more electron. So bond form near to that, reduction happen away from that. But the final product you end up with conjugated alkene, which is 1,4-diene. Again, it can be reduced by lithium and ammonia. We already seen the reaction map. So reduction happened. You have the final reduced product, which is 1,4 reduction. So if you look at the problem, you have two Birch reduction happen consecutively. Same reagent reacted twice. The concept you have to learn here is always you look for the functional group. Until the functional groups are available, the reagent reacts, you end up with multiple consecutive or parallel reactions. Then the next example, you have benzoic acid, lithium and liquid ammonia. You should find what will be the final product. Here starting metal is benzoic acid. Acid is the electron withdrawing group because of sp2 hybridized carbon. Because of more S character, it has 33% of S character. So it is more electronegative than sp3 carbon. So it acts as the electron withdrawing group. The electronegativity promotes the withdrawal. So the reduction happened near that. So 1,4 reduction happened. You have reduction. You have Birch reduction. The concept you have to learn here is acids are electron withdrawing group. Birch reduction happened near the acid. Then the next example, you have alpha naphthol, naphthalene with alpha position alcohol. You are reacting with lithium and liquid ammonia. You should find what will be the final product. The starting metal is naphthol. Naphthol contains OH. It is mesomeric in nature because lone pair can participate in the delocalization. Ring will become electron rich. Since the attacking species is electron, it always attacks less electron denser ring. So if you look at the electron density, B ring is more denser than A. So the possibility of A attack is more. So the electron repulsion don't allow A ring reduce. You have 1,4 reduction happen at the A ring. The concept you have to learn here is the reduction happen in the less electron ring in the fused starting material. The concept you have to learn here is in Birch reduction, the reduction happen always in the less electron denser ring. Then the example 7. Here you have quinoline, lithium and liquid ammonia you are using. You should find what will be the final product. Here you have quinoline. It contains fused system of benzene and pyridine. Lithium and liquid ammonia using mean Birch reduction reaction. The reduction happen at the nitrogen ring. Why? Because nitrogen is electron withdrawing in nature. In periodic table, it's near to the fluorine. So the reduction happen at the B ring. Why? Because electron withdrawal make the ring electron deficient. So B ring will be less denser than A. Since the attacking species is electron, it attacks the B, the reduction happen and you have the final product. Moreover, the reduction happen at the 1,4 position where nitrogen also reduce because negative charge can also stabilize by electronegative nitrogen. The concept you have to learn here is in quinoline ring system, pyridine ring is reduced in a fashion that nitrogen get reduced. Then the next example, you have benzoic acid. In ortho position, you have side chain with alkyne, which is cis fashion. You are reacting with lithium and liquid ammonia. You should find what will be the final product. Here starting metal is benzoic acid, side chain you have alkyne. There is the possibility of two different Birch reduction. Alkyne also get reduced, benzene also get reduced. That is the interesting fact about this reaction. So benzoic acid contains COOH. COOH is the electron withdrawing group. So the reduction happened at the 1,4 position. So 1,4 double bond forms. Next it has the possibility of alkyne. As we seen already in the basics, alkyne also get reduced. Since the mechanism is radical mechanism, radical anion form, due to the repulsion, trans product is stable. It's a very important concept. Only trans is formed here. So the concept you have to learn here is whenever you have the same system alkyne and benzene, two set of different Birch reduction reaction is possible. Then the next example, you have toluene, meta position you have methoxide, you are reacting with lithium and liquid ammonia. You should find what will be the final product. The question is interesting because you have two different functional groups but two have same property in nature. Both are electron donating because mesomeric effect on O-methyl group, hyperconjugation on methyl group, two different set of electron donation. How it can drive the product is the real question here. Here I given three possibilities A, B, C. But A is major because it is the middle ground between O-methyl group and methyl group. The reduction happen away to that. B is minor because reduction happen near mesomeric. It is impossible. Repulsion is more. C is minor because reduction happen near methyl. So the reduction is not at all possible. So only possibility is A. The concept you have to learn here is whenever you have similar functional group, always find the middle path between the both groups and identify the major product. Then the next example, you have benzene with two methyl group. They are in the ortho relation. You are reacting with lithium and liquid ammonia. You should find what will be the final product. Here you have two methyl group. Which group control the final product is matter here. Here the methyl group is there. It is electron donating in nature because of hyperconjugation. It can increase the electron density in benzene. Hence anion cannot form near to that. Here there are the two possibilities A and B. A is major, B is minor. Why B is minor? Because reduction happen near CH3 mean the anion form near CH3 it won't allow. So B is minor. On the contrary, if you look at the A, the reduction happen away from the two methyl group. So A should be the major. Since electron donating group don't allow the anion form near to that, so A is the major one. The concept you have to learn here is whenever you have non-competing functional group, always decide based on the middle reaction pathway. Then the next example, you have benzene and it has fusion with 5-member oxygen ring which is heterocycle, and you have O-methyl. You are reacting with lithium and liquid ammonia. You should find what will be the final product. Here benzene and sodium ammonia, it's a Birch reduction reaction, but how it is happen in the important thing. Here anion can form in many ways, but there is a one reaction pathway because anion cannot form near O. Since O has lone pair also electron, anion also electron, repulsion is maximum, so don't form near that. On the contrary, if you look at it, anion cannot form near O-methyl also since it is mesomeric in nature. So two possibilities you can avoid meaningfully by the repulsion property. So only pathway is radical form away from the O-methyl as well as O. Since two O groups are mesomeric, it is distant from both O-methyl group. So reduction happen, you have dianion, reduction happen consecutively, it quenched with H+. The concept you have to learn here is anion cannot form near the O because of lone pair and anion both are electron repel each other. It creates the regioselectivity. Then the next example, you have starting metal is cyclohexenone With alpha position, you have methyl group. It's a alpha beta unsaturated ketone. You are reacting with lithium, methyl iodide, and liquid ammonia. You should find what will be the final product. Here the conjugated ketone situation. So the reduction happened at the fourth position like Michael addition. Electron attacks the fourth position. The charge travels. You have anion. But anion can form with carbon. It attacks the methyl group. If you compare the nucleophile, carbon and oxygen, carbon will be the better nucleophile because of electronegativity. Oxygen is more electronegative. It cannot donate. So the anion form on the carbon, not on the oxygen. Anion attacks, you have new CC bond. So the final product is kind of alpha methylation. Then the next example, you have fused system. Anisole is fused with cyclohexanone. You are reacting with lithium and liquid ammonia. You should find what will be the final product. The present problem is interesting because it has the many possibilities. I given PQR 3 possibilities. P is not possible because anion form near the lone pair containing methoxide. So lone pair anion repels, so don't form. Unstable anion don't allow that. Then Q don't have any extra special stability. Even though it has the chances of formation, it will be the minor one. Major one will be the R. That's why we taken the pathway of R. Starting material sodium and ammonia attacks. Set pathway, diradical forms, then dianion forms. Then the formed anion will be stabilized by CO. CO is sp2 carbon. Electron withdrawing in nature, it stabilizes it. You have the final product with reduced hydrogen, where carbonyl near carbon reduce. The concept you have to learn here is whenever you have multiple possibilities, one way to identify the major product is analyze the anion stability. Then the next example, you have benzamide. You are using lithium and liquid ammonia. You should find what will be the final product. The product formation is similar like benzoic acid. Starting middle is benzamide. It's a carbonyl with amine. Carbonyl has sp2 hybridized carbon. It is electronegative because electronegativity of sp is higher than sp2 than sp3. sp2 is electronegative because of more s character. So anion formed near CONH2. The reduction happened the carbon near the amide group. So 1,4 reduction happened. The final product formed like benzoic acid. The concept you have to learn here is amide group is like acid group. The reaction proceeds like electron withdrawing group, end up with 1,4 reduction. Then the next example, you have benzene attached with trimethyl group. Silicon is the carbon analog, so trimethyl possibility is there. You are reacting with lithium and liquid ammonia. You should find what will be the final product. Here trimethyl group is there. The silicon is electron positive. It's like electron donor. It always push the electron out from the system. So consider it as electron donor. So anion cannot form near to it. So 3,6 reduction happen. The concept you have to learn here is silicon group is electropositive. It should be treated like electron donating group. So the reduction happen away. 3,6 position is reduced. You have the final product. Then the next example, you have trifluorotoluene reacting with lithium and liquid ammonia. You should find what will be the final product. You might know already, fluorine is the most electronegative element, highly electron withdrawing in nature. The starting metal carbon has 3 fluorine. It makes the ring electron deficient. So electron withdrawing pathway happen. Reduction happen near the trifluorocarbon. So the final reduction happen in 1,4 position. You have the final product. The concept you outline here is fluorine is the electronegative element. So the final product will be like 1,4 reduction. Then the next example, you have naphthalene. You are reacting with lithium and liquid ammonia. You should find what will be the final product. The reaction may look simple, but two consecutive Birch reduction happen because first reduction leads to the reduction happen at 1,4 position. Again it forms benzene ring because aromaticity should be established for the every step. Because of aromaticity, benzene ring form. So again Birch reduction is possible. You end up with 5,8 carbon reduction. So there are two reduction, 1,4 and 5,8 carbons are get reduced. Mechanism will be little bit harder. It will be like two consecutive Birch reduction mechanism. Better memorize it for quick and easy problem solving. Then the next example, you have para-dimethylbenzene. You are reacting with lithium and liquid ammonia. You should find what will be the final product. Here you have two electron donating group. So electron donating group don't allow the anion to form nearby. So double bond form near it, anion form away from it. So it is a typical 3,6 reduction reaction. Electron donating group promote that. So the concept you outline here is methyl is electron donating in nature because of hyperconjugation. So the reduction happen away from that. 3,6 reduction happen. Then the next example, you have benzoic acid, meta position you have O-methyl group. You are reacting with lithium and liquid ammonia. You should find what will be the final product. What is interesting about this question is electron donating and withdrawing group in the same ring. As we discussed, starting metal contain electron withdrawing COOH group, electron donating CH3O group. Finding the final product is tricky because you have to find the middle pathway. OCH3 is electron donating because of mesomeric. COH is electron withdrawing because of sp2 carbon. The middle path will be reduction happen near the acid because it can stabilize the anion. At the same time, it should happen away from the OCH3 because anion will be repelled by lone pair oxygen. So the reduction happen at 1,4 position. So it can obey both rule. Double bond form near OH3, form away from COOH. So the final product is plausible pathway. Here numbering given just for the reference, not a IUPAC numbering. The concept you outline here is whenever there is a competing functional group, we should find middle pathway for the final product. Then the next reaction, starting middle is cyclohexene. You have alpha, beta unsaturated ketone. Beta position you have methyl group. You are reacting with lithium and ammonia and allyl bromide. You should find what will be the final product. Here the starting middle is alpha, beta unsaturated ketone. So it will be like Michael addition. Electron attacks the fourth position and generate the nucleophile. If you look at the nucleophilicity, carbon is the better nucleophile because of less electronegativity. So it can act as the nucleophile. So it attacks, you have the bromine elimination. The elimination happened through the SN2 prime mechanism. You have end up with new CC bond. The concept you outline here is whenever there is a electrophile, Birch reduction can provide the nucleophile, end up with new unexpected carbon-carbon bond formation. Then the next reaction, you have benzoic ester. with methyl group on it. You are reacting with lithium and liquid ammonia. You should find what will be the final product. Here you have ester. Ester is like acid. It has carbonyl group. Carbonyl group contain sp2 carbon. If you look at the electronegativity, sp2 carbon is more electronegative than sp3 because of more s character. So it will act like electron withdrawing group. So anion can form near to it because electron withdrawing group stabilize the anion. So reduction happen at the first carbon which is near to ester. So 1,4 reduction happened. Electron withdrawing nature of ester promoting it. The concept you have to learn here is ester will be treated as electron withdrawing group. Promote the 1,4 reduction reaction. Then the next example, you have alkyne. Side chain you have propyl group on the both ends. You are reacting with lithium and liquid ammonia. You should find what will be the final product. Here you have alkyne. As we discussed, radical anion formation is possible. So triple bond will be reduced to the double bond, but only in the transformation. Only transform because of anion and radical in the adjacent carbon. Trans product is formed. Why you should know similar kind of Birch reduction mean? Whenever you design the bulkier or high level molecule, you should know all side reaction and possible functional group attacked by given reagent. Here lithium and ammonia do Birch reduction. At the same time it can reduce the alkyne. So you should know the adjacent reaction to master the high level synthesis. Then the example 23. Here you have spirene compound, 5-member and 6-member ring. 6-member ring contain alkene and 2 methyl group. 5-member ring contain alkene. Side chain you have ketone. Basically it's alpha, beta unsaturated compound. You are using lithium and liquid ammonia. You should find what will be the final product. Here you have alpha, beta unsaturated ketone which can be attacked by lithium and liquid ammonia. So the reduction happened Michael addition way. Finally you have reduced alkene. Here one thing you should know here is 2 alkene is there. Only 1 alkene is reduced which is in conjugation with ketone. Isolated alkene not reduced. It is called regioselectivity. 1 alkene selectively reduced. The concept you have to learn here is lithium and liquid ammonia selectively reduce the conjugated alkene. Then the next example, you have cyclohexenone, alpha, beta unsaturated ketone. 3 methyl groups are there which is in 3rd and 5th position. You are using lithium and liquid ammonia. You should find what will be the final product. Here the similar condition. So alkene is selectively reduced. Ketone is not reduced. So lithium and liquid ammonia selectively reduce the alkene which is in conjugation with ketone. Here also regioselectivity. Only alkene pi bond is reduced, not the carbonyl pi bond. Why we should know fact like this mean? If you want to design bigger molecule, you should know the fact that the reagent can attack conjugated ketone as well as conventional Birch reduction. Then the next example, you have benzene, acid and side chain you have trimethylsilide, lithium and liquid ammonia you are using. You should find what will be the final product. Here the question is about regioselectivity, where the reduction will happen. You have electron withdrawing group as well as donating group which will dominate. Basically balanced and optimized mechanism will be followed. Acid is the electron withdrawing group, so anion can form near it. It can stabilize the anion. Trimethylsilide is the electron donating group, electropositive in nature, so anion form away from that. So the reduction happen at 1,4 position. The concept you have to learn here is whenever you have competing functional group, choose the balanced and middle pathway. Then the next example. Here you have sulfur analog of indole. Third position you have acid, lithium and liquid ammonia you are using. You should find what will be the final product. Here two possibilities are there. A ring can be reduced, B ring can be reduced, but attacking nucleophile is electron. It is electron rich, so it prefer less electron denser ring. Theoretically, B ring should be electron denser because 6 electron in the 5-member ring, but COOH is electron withdrawing group, make the ring less electron denser, so density of A is higher than the B. So reduction happen at the B. It's the first regioselectivity. Then it only reduces on the second position because it is balanced both by sulfur and acid. Anion can be stabilized well. So the final product is reduction happen in the 5-member ring in second position. The concept you have to learn here is whenever fused ring system, two types of regioselectivity come. One is which ring will be reduced. Second is which position it will be reduced. Then the next example, you have conjugated diene which is butadiene, lithium and liquid ammonia you are using. You should find what will be the final product. Here you have conjugated diene. Similar electronic mechanism is possible. Radical anion form. Both anion and radical is separated. That's why 1,4 reduction. So the radical anion separated, you have alkene migration at middle position, terminal carbons are reduced. So basically the reduction happen at terminal. You end up with switching of pi bond. This is the kind of Birch reduction. Better you know this kind of reduction when you decide a bigger molecule because bigger molecule will have many functional group, many reaction possibilities. So lithium and liquid ammonia can attack and can react with conjugated diene. Then the next example, you have butane, middle position you have alkyne, you are using lithium and liquid ammonia. You should find what will be the final product. You have butane, lithium and liquid ammonia. You form radical anion. Radical and anion in the adjacent carbon. The carbon will become trans, both methyl group in trans position. The reduction happen in the trans way. You are reducing alkyne to alkene, triple bond to double bond, but in the trans position, it is a stereoselectivity. Technically, it's not a Birch reduction. As we discussed already, if you synthesize larger and big molecule with many functional groups. Then the next example, you have benzene fused with cyclohexane. Ether in the benzene ring. You are reacting with lithium and liquid ammonia and sulfuric acid. You should find what will be the final product. Here you have benzene and cyclohexane. You are using lithium and liquid ammonia. So the reduction possibility in 1,4 position. Since O-methyl group is mesomeric, it don't allow the anion form near to it. So reduction happen away from it. So the reduction happen away. Double bond form near OCH3. Then you are using sulfuric acid which can break the ether, form alcohol. Alcohol and alkene is nearby, it's enol. So heta-enol tautomerism is possible. Final product is unexpected ketone there. The concept you have to learn here is always look for the reagent and complete saturation of functional groups. Then the next example, you have indole, lithium and liquid ammonia you are using. You should find what will be the final product. Here two fused rings are there, A and B. Nitrogen contained ring is B ring. Here 6 electron is there both in A and B. Theoretically, if you look at it, A has 6 electron in 6-member ring. B has 6 electron in 5-member ring. So density of A is lesser than B. So it will be considered as electron deficient. Since the attacking species is nucleophile, it only attack less electron denser ring. Electron density of A is less. Reduction happen in the 1,4 fashion. You have the final product. Here two selectivity is there. The choice is between A and B. A ring is reduced, not the B ring. Then the next example, you have anthracene, lithium and liquid ammonia you are using. You should find what will be the final product. Here you have three ring system A, B, C. So which ring will be reduced or all will be reduced is the real question here. The interesting thing is all rings will be reduced. There is 3 times Birch reduction. 1, 4, 5, 8, 9, 10 position got reduced. So 3 times Birch reduction. The mechanism is mostly like benzene. So the reduction happened 1, 4 position in all the rings. Technically it's 1, 4, 5, 8 and 9, 10. The concept you outline here is benzene analogs like anthracene and naphthalene. All 1,4 position will get reduced like any other Birch reduction reaction. Then the next example. Here you have pyridine, benzene with nitrogen analog of it. You are using lithium and liquid nitrogen. You should find what will be the final product. Here pyridine is the starting material. Lithium and liquid ammonia you are using. Basically Birch reduction possibility. But where the reduction happen is interesting. Since nitrogen can be considered as electronegative, it can stabilize the anion. So the reduction happen at nitrogen as well as the 4th position. So nitrogen can be treated as electron withdrawing group. Final product is 1,4 reduction. The concept you outline here is pyridine also undergo Birch reduction where nitrogen and 4th carbon will be reduced. Then the next example, you have benzene with 1,4 position tertiary butyl group. You are using lithium and liquid ammonia. You should find what will be the final product. Starting metal benzene with tertiary butyl group. The tertiary butyl groups are well known electron donating group because of hyperconjugation and plus I effect. So the reduction happen away from that because electron donating group destabilize the cation. So reduction happen at 3rd and 6th position. Finally you have double bond near the tertiary butyl group. The concept you outline here is tertiary butyl group is electron donor. So the reduction happen away from it. Finally, we will see the summary of the Birch reduction. Benzene with electron donating group, the reduction happen away from it. Benzene with electron withdrawing group, the reduction happen with ipso carbon. Fused system like benzene, naphthalene, anthracene. Birch reduction will reduce all 1,4 positions. In naphthol, A ring got reduced. In quinoline, B ring got reduced. In indole, A ring got reduced. You should know all the regioselectivity while doing the reduction.